Good evening, all. I hope you all doing well. We'll start the day two session. Rajesh sir, good evening.
Yeah, good evening, ma'am.
Yeah, you can start the session, sir.
Done, ma'am. Yeah, hello everyone. So, hope I'm audible and the screen sharing is also working. Can you confirm that with a yes in the chat box? Hope
Yes,
I'm
sir,
audible.
it is. Yes, sir. It's audible and visible as well.
Done, ma'am. Okay, well, yeah, we'll make the group chat and make meeting chat enable. That's fine. Now, guys. Now, see, yesterday we have talked about introduction to data structures. We have seen simple examples of data structures that we are having. We have gone through real world examples. We have gone through technical examples. I hope you got a good idea and just an overview of how data structure generally looks like and why do we have these many data structures? What do we actually do in it? You have any doubts in yesterday's session? Any doubts? Anything that you want to talk about in yesterday's session? Any doubt in yesterday's session? Right? So do let me know whenever you have any doubt, since we have like almost near to 1,000 people or so. Okay, your doubt may miss a little bit, but try to post it whenever I'm looking at the chat box. If you share your questions and all, I'll be able to answer them. Done? Right then. So today we'll be going to the next part of it. We'll talk about algorithm. We will talk about what is time complexity, what is space complexity. Okay, it's very important for you to understand how to evaluate a code. Let's say you have written a piece of code. You need to understand whether it is a good code or not. Okay, we need to grade it. We'll be talking about how we can evaluate a given code. Done? That's it. That's what we'll be doing. Let's get started. I'll be coming back to this chat box every now and then. Okay, yesterday I have seen that you guys complained about video a little bit. I have seen like two panels are being displayed, so I'll not be having that on today. Done. Let's go ahead. Let's get started with time complexity and space complexity. Okay. Now, see, before we get started, this is what I'm going to convey here in this session. We'll talk about what is an algorithm. We'll talk about performance analysis in the sense time complexity and space complexity. We'll talk about how to evaluate it, what is big O notation and all. That's what we are going to go through. Okay, we'll go through asymptotic notations. In that, we will be specifically talking about big O. That's all. That's all you need to know. For the rest of the sessions, we need that big O notation. We need to know how to, okay, evaluate our code. That's it. Now, see, coming to algorithm. So, what is an algorithm? What is an algorithm? What is an algorithm? Any idea? What is an algorithm? Yeah, I got a lot of good evenings. So, what is an algorithm? Yeah, why I'm getting this as a separate window pop out? Yeah, we'll pop it out. What is an algorithm? Very good step-by-step process. Okay, step-by-step process to complete any task. Yes, perfect, correct. Okay. Now, see, yeah, facing some issues. Good. Right. Now, coming to an algorithm, as you said, algorithm is a set of well-defined instructions in a sequence. If you follow those instructions, when a machine follows those instructions, it will be able to complete a task. Okay. There are some qualities for a good algorithm. I see. I'll talk about it. I think we are getting the example. Yeah. Let's say whenever you want to make a cup of tea or so, what you will be doing? I think this is fine. Yeah. Just a second. Yeah. You see here we have a process. First, we need to have a kettle. We'll be boiling some water in it. We'll be having our tea bag. Okay. We'll be having our milk. We'll be having our sugar cubes. We'll be adding them. Okay. All of it in a piece of coffee mug or the tea jar, etc. And all. That is where we will be having it. So we have a step-by-step process. Imagine if I forgot any step or if I do anything before the other. Okay. The entire process will be ruined. Okay. That's what we'll be having. So step-by-step process we have. Coming to an algorithm, we will be following a sequence of steps to solve it. If you miss any step, or if you do not do that, you'll not be able to get anything. Whenever we solve equation, we'll try to come up with the step-by-step solution for it. Okay. So these are some of the good qualities of an algorithm. You see, first thing, input and outputs of the code should be defined very precisely. Whenever you're trying to solve a question, you need to know how many inputs you are taking and how many outputs you need to display. And every step of the algorithm that has to be clear and it should be unambiguous. Unambiguous in the sense it should not lead to multiple outcomes. Okay. Let's say you're traveling by a car, autonomous vehicle it is. Okay. Automatically, if you enter the destination, it will take you to your destination. Now, in that, depending on your destination, let's say there is a Y junction, it should take a decision that it should either go to left or it should either go to right. Okay. But if it tells you both left and right, then what will happen? You'll directly hit the divider, right? So that's what. Every step should be clear. It should not give you multiple solutions. Okay. And algorithms should be effective compared to many other ways of solving. There will be different ways of solving a question, and the algorithm that you are selecting should be very efficient, should be better than all the other ways. And you see, algorithm is not any computer code. We will be talking about it just like any other normal language, English, Hindi, whatever you want. Okay. It's just a step-by-step process. Just like you and your friend are going to communicate regarding any task, that is how we will be communicating about it. We just need to convert that into whatever language that you are using, Python, Java, C++, anything. Okay, we'll be able to convert. Then that's it. That's about the introduction to algorithm. Let's talk about analysis. You see, whenever you have any algorithm, there will be a best case analysis, there will be an average case analysis, there will be a worst case analysis. Now, so what are these things? Let's take a small example. Let's assume, okay, I have a small cardboard box, and this box contains some 99 numbered balls in it. Okay, you see, I have a cardboard box. In this, I have a lot of balls in this manner. 1, 2, 3, 4, up to 99 I have. Okay. Now imagine I want to guess a random number. I'll be closing my eyes. I'll be keeping my hand inside the box. I'll be picking a number. Okay. What are the odds of getting the number that I am guessing in the first guess? Okay. You see here, we have all these boxes. Let's say, assume the number I want is 1. I guess for 1. I wanted 1. You see, I'll be closing my eyes. I'll be keeping my hand inside the box. I'll be picking it out. So see here, the first number I am getting is 1. So that's it. You see here, I don't have to perform any other operations. This is what we call as best case scenario. This is what we call as best case scenario. Okay, best case in the sense, given 100 values or whatever it is, if you are getting the answer in the first iteration itself or as soon as possible, that is what we call as best case scenario. Yes, so what happened? You guys are unable to see anything. I hope screen sharing is visible. Everything is fine. You're able to see that box, etc. and all. Just a small confirmation. Yeah, done. And talking about the slides and all, you'll not be getting any of it. These are all animated content. I've been working on them a lot. So you can take a note of everything. Just record them in your brain. That's it. Done. So see here, that's what we call best case scenario. Let's talk about average case. See here, we have the same cardboard box. I want the number 70 to be picked. So first try, I closed my eyes. I picked a ball. The number I got is 1. So it's not the ball I want. So that's the first ball I have picked. Second try again. I have closed my eyes. I picked a ball. I got 30. It is not 70. I'll do it again. Okay. Third try, I'm doing it. I'm getting 52 this time. Fourth try, fifth try. It can be any try. Okay. It can be any try. I have 100 balls here. It could be anywhere from 2 to 99. You see here we are getting 70. That is the ball that we are looking for. So it took us 4 tries or 5 tries, or it can took you 30 tries or 40 tries on an average. Okay. So it can take you n number of tries, anywhere from 2 to n minus 1. That's what we call average case. Okay. Now let's talk about let's talk about worst case scenario. Worst case scenario in the sense, if you have a luck like me or so, you'll be ending up with this worst case scenario. Let's say I have the same cardboard box. Again, same thing. The ball I want is 69 this time. I'll be closing my eyes. I'll be picking up a ball from the cardboard box. You see, I got one. It's not the number I want. I'll do it again. Okay. I got 30 this time. That's not the number I want. Okay. Again, I'll be doing the same thing. I'll pick another ball. 52 it is. It's not the number I want. I'll keep on repeating this process. You see, 70 we got this time. I'll do it again. So this time, you see, I'm getting 90. If you keep on repeating this after an eternity, see here, now we are getting 21. That is our 97th ball that we have picked. 98th ball we got is 69 also. Okay. So if you have n number of balls present inside of it, and if you are getting it, if you see here, if you are getting it for the first time, like first time you're picking up a ball, you're able to get the ball that you're looking for. That's the best case scenario. After picking up 98 balls, if the 99th ball is 69, means you have done all the operations. That is what we call worst case scenario. And on an average, you can pick the ball that you're looking for in between 2 to 98. Okay, that is what we call average case scenario. Okay, just keep these things in your mind. I hope you understood a little bit about okay, best case, average case, and worst case. We'll be using this a lot. Just keep this in mind. Imagine you have a ball. If you are getting it for the first try, best case. Last try, average case. Sorry, worst case. Any other tries in between, average case. Done. That's what we have complexity. Now, complexity is of two types. Okay, we have time complexity and we have space complexity. And coming to the definition of complexity, you see, complexity in the sense it's about how an algorithm uses the resources that we have. It's about time and space, how much time it is going to take, and how much space it is going to occupy. Okay, that is what we call complexity. So we will be talking about time complexity and space complexity. Done. That's it. We have time and space complexity. Let's first talk about space complexity. It's a bit easy and it's very easy for us to go through it as well. So see here, coming to space complexity, what is meant by space complexity? How we are going to calculate space complexity? Just go through the definition a little bit. How we will be calculating space complexity? How we will be calculating space complexity? Just go through that small. See, we have two things in space complexity. We have something called fixed part and we have something called variable part. Just go through that. We'll be talking about it. Oh, shit. Mhm. Getting chat previews. Mm, Not this one. The meeting window only. Maybe that will help us. I'm sorry. Just a second. Just figuring out the chat. Show chat previews. Let's close it. Yeah. Maybe I'll pop it up. Done. Done. Yeah. You see here. Now everything is fine. Yes. Now, coming to space complexity here, you see, space complexity of an algorithm is nothing but it's about how much memory space it is required by it. And generally, we calculate it in two ways. We will be having something called as fixed part and something called as variable part. Fixed part in the sense, you see, it's about how many variables you are using. Okay, whatever you for your for loop for your okay normal storing and all, you will be having some constant fixed values. That's what we have as fixed part. Variable part depends upon the input size and all. Okay, variable part depends upon the input size and all. For example, if I'm giving you n is equal to 10, you need to take an array of 10 elements. Okay, n value is fixed. We need to take the size of it. For if the user is giving us 10, we need to take 10 values, 10 integers also. That's what we are having. Now, see, coming to space complexity, as I said, let's take a small example to go through all of it. Let's say I have a small function. This is just an algorithm. Okay. So we have a function. If you observe here, how much space is it occupying actually? How much space do you think it is occupying actually? Can you come up with the space values for it? Okay. Can you come up with the space value for it? Don't worry, I'll address all your queries. Okay, for now, let's try to complete space complexity, time complexity a little bit. By the end of the lecture, everything that you are mentioning will be covered. And if you still have any other queries, I'll address them. Okay, so first let me finish, then we will go through all your queries and all. That will be fine. Then, so what is the space complexity for this one? Anyone? Let's assume integer is taking 4 bytes of memory also. Okay, so how much space do you think it is going to require? How much space do you think it is going to require? Let's say integer is taking 4 bytes of memory. Okay, tell me 10 bytes. You can write it in O of n, etc. and all. That's fine, but let's talk about it in bytes as of that. Yes, very good, very good. All correct answers, fine. 12, 16, etc. Big O of 1, that is also fine. Constant time complexity. You see here, I have the variables A, B, and C. They all will be allocated some memory. Okay, that's total 4 plus 4 plus 4. We will be having 12 bytes of memory. Along with that, we are also using the variable Z as well. Okay, so that will again take 4 bytes of memory. Done. And also this return value also takes 4 bytes of additional memory. That's a different topic. But anyway, let's say it is occupying some 16 bytes of memory or 20 bytes of memory. Okay, so this is not going to change. Doesn't matter how many values that you enter. Okay, it is just going to take A, B, C, Z, and that returns it. That's it. Total 20 bytes only. Actually, that's it. Okay, now let's take one more scenario. Let's take one more scenario. Let's say I have another algorithm. Okay, see, this is calculating sum of all the values of an array. So as I said, see how many bytes it is going to occupy. Here A is the size of the array, like A is the array itself and n is the size of the array. Now n is just an integer. It is going to take 4 bytes of memory only. Now the array that you are taking, if I am giving you an array of size 10, it is going to occupy 40 bytes of memory. Okay, 10 integers. Each integer occupies 4 bytes of memory. So 40 bytes of memory it is going to be. If I'm going to give you 20 values in an array, it will be occupying 80 bytes of memory. Okay, it depends on the input size of the array. So how much memory is this going to require? You see, it is going to require 4 into n, means 4 bytes of memory per integer. We'll be having n values in our array. So 4 into n it will be. And 16, why 16 means, you see, result is an integer. It is going to occupy 4 bytes. I is an integer. It's a constant value. It is going to occupy 4 bytes. N is an integer. It is going to occupy 4 bytes. And again, that return results is there, na? Okay, that will also occupy 4 bytes. So total 4 plus 4 plus 4 plus 4, 16. And coming to the array, if I'm giving you 10 elements, it is going to be 4 into 10, 40. 20 elements, 4 into 20, 80. That is how it is going to be. So 4n plus 16 it will be. Now, what is the fixed part and what is the variable part here? Now, what is the fixed part and what is the variable part here? What is the fixed part and what is the variable part here? Now, A is an array. A is an array of size n. Okay. So, what is the fixed part and what is the variable part? You see, yes, 16 is the fixed part and 4n is the variable part. Okay. Because array, whatever input that you give, it is going to modify according to that. Okay, that's what we have. So this is what I was talking about. Given any input, While talking about the space complexity, we will be calculating how much of space is occupied by each and every value that you have. It will be having fixed part and variable part. Fixed part, they will be the same. Doesn't matter. It will not be dependent on the size of input that you are giving. But variable part, array, if I'm telling you 10 values, it will take 40. 20 values, it will take 80. So that is what we call variable part. Okay, that's how we generally calculate. We'll talk about how to reduce it and all. Generally, space complexity is never a big problem. Okay, time is the one that we need to worry about. For some questions, in order to reduce, like for most of the questions, in order to reduce time complexity, we use extra space. Okay, so that's what we will be doing. Maximum, whatever algorithm that you write will be good in space complexity only. In order to reduce time, we will be using extra space. Okay, that's it. That's about it. Now let's talk about time complexity. Now see here, see here. Let's say we'll have a small exercise for it, a small brainstorming question. Let's say I will be dividing you all into two small groups. Okay, I've given you a simple task. The task is you need to calculate sum of n natural numbers. You see, group one, they have calculated it. Okay, this is the solution they have given. Group 2, they have calculated it. This is the solution they have given. Okay. Are both the solutions correct? Are both the solutions correct? Are both the solutions correct? Yes, both the solutions are correct. Okay. Both the solutions are correct. Now, how I will be evaluating which code is better? Group 1's code is better or Group 2 code is better? Group 1's code is better or Group 2 code is better? Group 1's code is better or Group 2 code is better? It is actually Group 1. Why Group 1 in the sense? See here, let's say whenever you are given a question, there will be multiple ways to solve it. There will be multiple ways of doing the same task. Now, whenever you come across a situation where you have two or three different types of solutions, you need to come up with the optimized one. Optimized one in the sense, you see, generally the better code, we will be talking about it through this criteria. Okay. First thing, we will check whether both the solutions are correct or not. Yes, for all the inputs, we are getting the correct answer, then both are valid solutions. Now, what else I need to check? I need to check, okay, I need to check the code should be readable. Whatever inputs that you are writing, you should be able to get the output for all of it. Okay, the code should have fewer lines of code, readable, as I said. Now, the next thing, the code should run very fast. It should take very less time to execute. And the next thing, the size occupied by your code should be very less. Means the time taken by your code should be very fast, and the space occupied by your code should be very less. Okay, that's what we are talking about here. So, which one do you think is going to take less time? Which one do you think is going to take less time and less space? Less time and less space. Which one do you think is going to take less time and less space? Yeah, group one, obviously. Why group one? You see here, for group one, assuming every single line of code operation takes 1 second or 1 unit, one operation, you can say. In order to take input, how many times we are taking input? Only one time. How many times you are calculating this operation? Only one time. This expression will be evaluated one time. And how many times you are displaying the output? One time. So how many operations it is taking? Three operations only. Doesn't matter if I give you n value as 10, n value as 100, n value as 1000. It never depends on input. Any given number, you will be able to get the answer in three operations. That's it. We'll talk about it. We have a very good discussion for it. I'm just giving you an idea about what is time complexity or how we are identifying better code here. That now see group 2 here. Taking input, one operation, sum equal to 0, one operation. Now here I am generating 1 to n numbers. Okay, if I'm giving you 10, it is generating 10 numbers. It is adding all the numbers manually. So how many operations is it taking? It's going to take a lot of operations now. Just ignore, like the first one is going to be 3. So here for n equal to 10 only, it is going to perform some 20 operations also. 10 numbers will be generated, 10 numbers will be added. That itself is 20 and extra 3 I have. So 23. If I give you n value as 100, it is going to generate 100 numbers, means 100 operations. And it is going to add 100 numbers, means another 100 operations. So 200 here. So see, obviously the first code that we have, okay, is executing everything faster. It's taking less number of operations. Okay. Now, if you have observed, I've been talking about operations. I have not been talking about seconds also. Okay. So you should not be deceived by the name. In time complexity, we do not calculate time. Okay. Let's talk about it. Let's go through that. See here, as I said, coming to time complexity, how we can calculate it. Okay. So let's see that. Let's go through a small, okay, selection here. Let's say I'm giving you two choices. Let's say I want to gift a laptop to you. Do you want a 8 GB RAM system or do you want a 16 GB RAM system? Which one do you generally prefer? You want a 8 GB RAM one or do you want a 16 GB RAM? 16 GB, very good. Okay. Do you want a i3 processor CPU or you want a i7 processor CPU? Which one do you prefer? Which one will it be? i7, very good. Okay, you're making good choices. Do you want HDD or do you want SSD in your system? You want HDD? Do you prefer HDD or SSD? Obviously, SSD is better. Okay. Now, can you tell me why did you make these choices? Why did you make these choices? Why 16 GB? Why i7? Why SSD? Obviously, they are costly, but why they are costly? Like, why do they cost more? Why do they cost more? Why do they cost more? Yes, they are very fast in execution. Now, listen very carefully. Listen very carefully. If I take a piece of code, if I run it in that 2000s machine, you see, we used to have a big monitor inside our schools and all. Okay. If I run it in that particular piece of, like, in that machine, if it is taking 20 seconds or so, okay. If I run the same code in a modern machine with an i7 processor, 16 GB RAM, SSD and all, it is going to take you less than a second. Here the code did not change. The code did not change. Okay. The code, the machine which runs it has changed. Okay. Your execution speed depends on your hardware. If you have a 8 GB RAM system, it will be performing all the operations a bit slower. If you have 16 GB RAM, speed increases. Your computer can perform 10 to the power of 8 operations per second. Okay, the better machinery, the better pieces of hardware you have, the better it will be able to perform those operations. Okay, so what I am trying to convey here is, in time complexity, will not be able to measure anything with actual time. You might think, sir, I'll be taking a stopwatch. I'll be clicking on start button whenever I run any code. Whenever I get the output, I'll click on stop button. No, it doesn't work like that. It does not depend on system time. Or you might think, sir, I'll be using an online compiler. Online compiler will use your device RAM only. Browser uses your RAM only and it depends on internet speed. So you cannot use that one as well. Okay, then what you will be using? We will be counting the number of operations. In time complexity, we will be counting the number of operations, will not be calculating time. Don't be deceived by the name. Okay. Now, sir, what are you saying here? You see here, let's say I'm present in Hyderabad. Okay. If I want to visit Delhi, if I want to go to travel to Delhi, if I take a bus also, okay, let's say it is going to take me some 30 hours or 40 hours. If I take, if I go by walk, it will take me 12 days, 15 days. If I take a helicopter or if I take a flight, it is going to take me 2-3 hours. Here, the distance did not change. The distance I have to cover from Hyderabad to Delhi will be somewhere around 600, 700, 1000 kilometers, let's say. The distance did not change. Okay, the mode of transport has changed here. You see, that's what we are talking about. Whatever piece of code that you are writing, if your machine has better specs, if your machine has good software, hardware, okay, it will always run it faster. We'll never be able to calculate it depending on system time. So what we will be calculating? We'll be calculating the steps. If a program takes 100 steps to complete, 100 operations to complete, in order to calculate that 100 operations, If you are having a good machine with higher specs, it is going to always calculate it faster, but the number of steps will not change. Just like distance between 2 points is measured by kilometers, not by time. This is what we are actually doing here. Okay. So we need to talk about how many steps that are involved. Okay. In a code. You see here, coming to this question again, as I said, the below one, if I'm taking n is equal to 10, I need to generate 10 numbers. I need to add all those 10 numbers. So again, 10 steps for generating, 10 steps for adding we have. So total 20 iterations we have, 20 steps we have. And displaying that number, taking input sum equal to 0. Again, 3 more operations we can say, total 23 steps. But if you consider the above one, you see here, we just need to calculate it only once, take one input, calculate or evaluate that expression, display that output. It is only going to take 3 operations. Doesn't matter what number you give. It is always going to take 3 operations. Okay, so which one is having the best time complexity? Whatever is having the less number of operations, that is the one which will be having the best time complexity. Understood about a little bit about time complexity and space complexity. Okay. So coming to space complexity, we will be calculating how much space is occupied by our entire file. Coming to time complexity, we will be calculating the system time, or we will be calculating the number of operations. Which one? We will be using a stopwatch, we will be calculating the start and end time, or we will be going through the number of operations. Yeah, that's it. So I hope you all are keeping these examples in your mind, right? Now let's go through, okay? Asymptotic notation. So before we get started with that, before we talk about big O analysis, before we talk about this time and space complexity only, it's not done yet. We'll be taking a piece of code. We will be, okay, analyzing which category it will fall under. We will talk about it. So before we get started, do you have any doubts till this point? I have seen you asking some doubts in that, okay, chat and all. So do you have any doubts till this point? Do you have any doubts till this point? Do you have any doubts till this point? This is your chance. Okay. This is your chance if you have any doubts till this point. Space complexity is nothing but how many bytes of memory you're actually calculating. Okay. You can just write down that number. Space is again not that much important. Always time is important. So don't worry. Once we go through this presentation, again, I'll ask Vivek if you have any doubt related to space complexity, we'll talk about it. Okay. So don't worry. Once let me complete and go through this one, then everything will be clarified. Okay. Yes, don't worry. We'll talk about worst case. In any interview, how to answer if asked to calculate time and space complexity? Yes, that's what we are talking about now. Time complexity means you will be calculating how many operations your code is going to take. Whichever code will take less number of operations, that is the one which executes faster. That's having a better time complexity. And coming to space complexity, if your code occupies less bytes of memory, that's it. That is the better code. Okay, if it is occupying less space, that's better time space complexity. No, don't worry, don't worry. We'll be talking about these things. Let's see. Now, see here, coming to asymptotic notations. You see what is meant by this asymptotic notation. Generally, we have this inside something called as design and analysis of algorithms. DAO we call it. You might have that subject, you might have seen it, or in future you will be coming across it. We'll not be going that much deep into it, because we are here to talk about data structures and algorithms. I'm just including this topic such that you will know what is meant by good code. Okay, how to evaluate good code. Now, what is meant by asymptotic notation? See, asymptotic notations means these are mathematical functions, mathematical notations, where we will be talking about the runtime of an algorithm. Okay, so we will be having a lot of mathematical functions here. Okay, in all of this, we are mostly interested in big O. And why big O? You see, why big O means big O will always talk about worst case analysis. Let's say you have built a small machine, you have built a piece of software. Let's say you have built that guess the number, okay, game also. You have 100 numbers, you're generating 1 to 100 numbers. Let's say you have delivered that to the client. Will you be saying that, sir, you guess any number, you will be getting it in the first try? No. Or can I say that, sir, you guess any number, you'll get it in 30 tries, 40 tries, 50 tries? No. We have to give him the worst case scenario. Worst case, it will take him 100 tries. Okay? It will take him 100 tries. 1 to n numbers, n number of balls we have, n tries it is going to take. We will need to always talk about worst case scenario. When things are not going good, you will be taking n number of operations. Okay? Worst case we need to talk about. That's what Big O will be going through. Let's see that. Let's talk about it. Let's go through everything. And let's see how we can calculate or analyze the time complexity. For now, before getting started, I want to mention something. You see, we will be taking every operation, okay, as one step also. Every operation is one step also. Just a second. I have a small charging problem. That's it. You see here, just a second. We have different algorithms which will be solving the same problem. Okay. But they all are going to take different time. Just as the previous example, as you have seen, we have two ways of solving a given problem. But the first one is faster, second one is a bit slower, but both of them are giving us correct answer. In asymptotic notations, what we will be doing is we will not be dependent on the hardware, we will not be calculating the system time. Okay. We will be focusing on how your algorithm will grow. How your algorithm will grow with the given input value. That is what we call rate of growth rate, you can call it. Okay. If you have a better machine, it will perform better. If you have a normal machine, it will perform normally only. Okay. Let's talk about it. Let's see before we go into that. Okay. Let's see how we can generally calculate. As I said, we'll not be calculating the measuring asymptotic analysis in seconds. We will be counting the number of executions. Okay. And how we are calculating all these executions? We will be calculating all these executions based on some small rules we have. See here, just have a very good look at it. Let's say every simple statement like taking input or displaying output or assignment or performing a small simple evaluation of an expression. Okay. All of these things are taking one single operation. If you have a loop, if you have a loop, let's say the loop is running for n times, 1 to n times also, it is taking n number of operations, we will say. The elements inside the loop will also be executed for n times. Okay, they will be also will be executed for n times, so n number of operations. Let's say we have a loop inside a loop. The outer loop, if it is running for n times, the inner loop, if it is running for n times, outer loop will make the inner loop run for n into n times. Nested loop, na? Okay. So that's why we'll have an example for all of this, just giving you a general idea. I know we have first years, second years, third years, final years. Some of you will be able to understand these things because you guys have started coding early. You are very much into it. You are at a good level. Some of you are beginners. You are just getting started. So I'm covering everything in beginner's point of view. Okay. So I hope you have gone through all of them. You had a good look at it. Let's understand this through some simple programs. Let's see how we can actually calculate time and space complexity, how we evaluate or grade a code. Let's say we are taking this particular piece of code. This is written in Java. I got an instruction that we need to go through Python a bit, but these are very simple. Let's remove all the complex part. Let's remove that class, public static void main, that etc. and all. You see, I've removed everything, that scanner class, etc. Now, this is the code we have. As I said, every simple operation will be taking how many operations? Every simple calculation or line will be taking one single operation, right? So, how many operations will the first line take? System.out.print enter in. It will be taking one operation. Okay, first one will be taking one operation. What about the second one? N is equal to sc.nextInt. We are taking a number input from the user. How many operations it will take? Very good, one. Okay. And system.out.println. We are just displaying it on the screen. I have written it in two lines, but it's single line only. I did not have any space in the presentation. So it will also take one operation. So how many operations it is taking? 1 plus 1 plus 1. So for any given n value, you are going to take how many operations? You are going to take 3 operations. That's it. Let's say I'm giving you n value 10, n value 100, n value 1000. It will be taking 3 operations only. It doesn't depend on the input n value. Okay. It is always giving you constant number of operations. This is what we call as constant time complexity. This is what we call as big O of 1. Okay. Or big O of n power 0. Big O of n power 0 is nothing but 1 only. Right. So that is what time complexity we'll calculate generally. This is what constant time complexities. Okay. So n power 0 or big O of 1, that's how we call it. Now let's take one more example. See here, I have another example. We have to print a multiplication table. That's what we are doing. Okay. Done. Now see, let's remove all the complex part. Again, how many operations for the first line? How many operations for the first line? How many operations for the first line? Very good. One operation. Perfect. How many operations for the second line? How many operations for the second line? Very good. One operation. How many operations for the third line? Third line in the sense this for loop here. How many operations? How many operations? How many operations? Yes, very good, very good, very good. 20, 21, 23, all are fine. But see here, see here. Generally, generally, how many operations will it take is, you see, initialization, I is equal to 1, it will be one time. That loop condition will be checked 20 times. For 20 times, it will be true. For the 21st time, it will be false. And every time, I value will be incremented. So it is going to execute how many times? 42 times actually, but fine. It doesn't matter anyway. Ultimately, you will understand. You can call it 20, you can call it 20 times. That's also fine. So total 42 times it's being executed. Now, what about the statements inside the loop? The statement inside the loop, we have a simple print statement where we are printing n into I is equal to n into I. Okay, 5 ones are, 5 twos are, 5 threes are, that's what we are printing. So it will be executed 20 times exactly. So how many times it will be? Given n value, any n value, 5, 10, 15, 20, 100, 1000, it doesn't matter. It is always going to be executed how many times? 64 times. This is also not varying with the given input. This is also constant with respect to the input. This is what we call as constant time complexity. Big O of 1 or big O of n power 0. This is also constant time complexity. Hope you got a little idea about calculating time complexity. Got a little idea? Cool. Can we move forward? Yeah. Done. Done. You'll get good idea. I'll be pacing everything. Okay. Once I complete a session, you'll not be having much doubts. If you still have, then you're happy to communicate. Okay. Done. Now let's calculate some more time complexities. Let's evaluate that. And moving forward, when we solve DSA questions, we will be talking about time complexity there as well. So it's not like this is the first and last session for time complexity. We'll keep on continuing this. Now see here, can you tell me how many operations the first line will take? How many operations the first line will take? One. How many operations second line will take? One. Now what about the loop? What about the loop? How many operations the loop will take? How many operations the loop will take? Very good, very good. Generally, if I have to go through it, you see, if I have to say I initialization will be done for one time. N will be checked n plus 1 times. And again, I will be incremented n times. So n plus 2 it will be. So 2n plus 2. But you can ignore all of it. You can, like, we generally call it n plus 1 because it doesn't matter much. Okay. So you can call it n plus 1. It doesn't matter much. You will understand. You will understand. Don't worry. Have some patience. You will understand at the ending. Okay. As a beginner, you will be having a lot of doubts in this manner. I do have. That's why I have such a presentation so that I have a lot of clarity. I got that clarity after struggling and going through a lot of books. So don't worry. Yeah. So I hope, yeah, what's confusing for you? So I is equal to 1. We are initializing it one time. Okay. And I less than or equal to n. We'll be checking it for n plus 1 times. N times it will be true. And the next time it will be false. So n plus 1 it will be. And I will be incremented n times. So totally that is n plus 1 plus 1 only. So 2n plus 2 only. That's what it is. Okay. That's what I have explained as well. So 2n plus 2 it will be. Now, how many times the value inside the loop will be executed? How many times it will be executed? How many times it will be executed? N times. The loop will be true for n times. It will be executed n time. And how many times the statement outside the loop will be executed? It will be executed only one time. So what is the total here? Calculate all the operations. How many times we are executing everything? So 1 plus 1 plus 2n plus 2 plus n plus 1, that is 3n plus 5. So now here we got an expression. Now whenever we have any expression, you see, we will be making some modifications. There are some points that you need to understand. Okay, how we will be evaluating or how we will be talking about such type of expressions. See, first thing, whatever expression that you have, okay, we will be ignoring all the constant terms. We will be ignoring all the less dominant terms. We can discard all of it. And we are only going to come up with okay, the most dominant term in it. Okay, ignore the constant terms, ignore the less dominant terms, ignore the coefficients of whatever dominant term you have. Okay, you can ignore it. We are assuming that the value of n that you are taking is very large. Okay, and one more point I would like to add here is, whenever you are talking about time complexity, listen very carefully, you will get good clarity, then I'll be addressing your doubts. We are always comparing n with n square complexity, or n square with n cube complexity, or n with log n, or n with constant also. We are comparing two different growth rates. If you are talking about the same growth rate, the calculation is going to be a bit difficult. Okay, we need to include all the factors. For now, what I mean by all these 4 points: ignore constant terms, ignore less dominant terms, ignore coefficients. Consider the input n value that you have is very large, is pointing towards infinity, is tending towards infinity. And we are comparing different growth rates. Now, let me take a small example for this. Let's say here, let's say we have this small expression that we have, okay, 3n square plus 5n plus 2. This is the calculation I got after going through a program, just like we got 3n plus 5, same way 3n square plus 5n plus 2 I got. Okay, if I consider a very large input size, for example, let's say I have taken 10,000. Okay, for 10,000, for n value is equal to 10,000, how many operations it is going to take? It is going to take 3 into 10,000 square plus 5 into 10,000 plus 2. It is going to perform these many number of operations. For n is equal to 10,000, it is going to perform these many number of operations. Now, if you look at the contribution of 5n and 2, okay, in this bigger value that we are getting, in the number of operations that we are performing, okay, you see here, coming to the contribution of 3n square, it is contributing 99.98% of the entire operations that we are doing. If you talk about 5n, it is contributing very less, kind of like almost 0.01% it is. If you talk about 2, the number of operations we have is even lesser, 0.000007% also. Since 5n and 2 are contributing very less, okay, we generally ignore them. We don't even have to talk about them. So we ignore 5n and 2 when we are talking about it. Okay, the most dominant term is 3n square. Again, I told you that in this 3n square as well, we need to ignore constants. Okay, you might ask, sir, coming to 3n square, you said n, if I'm taking 10,000 square into 3, that is going to be a very large number now. Now, why should we ignore it? You see, why we ignore it means, generally, whenever we calculate time complexity, okay, when we are talking about it, we will be talking about the rate of growth, right? Rate of growth. So let's say we have a small graph here. Done. Just a second, I'll grab my digital pad. Grab the digital pad. Done. Let's say we have this graph here. Done. If I am taking the input n value, okay, this is the input n value and this is the number of operations that we are doing for it. Let me write it down. This is input n. These are the number of operations that we have. If you plot your input value on x-axis and the number of operations that it is taking on y-axis, that is what we call rate of growth. That is what we call rate of growth. Okay, rate of growth. Whenever I'm talking about an algorithm, I'm talking about how it is growing with input and value. And what did I tell? This input and value is tending towards infinity. It's a very big value. Why a very big value? If you take Amazon, if you take Netflix, if you take Zomato, if you take Blinkit, the number of users that you have are very large. We are not talking about hundreds or thousands. We are talking about millions and billions. So whenever we are designing anything, we are assuming our input would be always tending towards infinity. We'll not talk about small values, 10, 20, 30 are for understanding purpose. But ultimately, you're running it for a very big n value. That is what we need to look for. Now let's continue with this one. Let's say n value equal to 10. The number of operations will be 10. It is linear complexity. The number of operations that you are taking are n. So n is what I got. So for n, I'm plotting the graph. You can check it out. Okay. If I'm giving you n value as 30, I'll be getting 30. If I'm giving you n value as 40, I'm getting 40. N value as 50, I'll be getting 50. That's it. Okay. Let's say I got the number of operations as 2n, or the number of operations as 3n, or the number of operations I have to do as 4n, or in our earlier case, we got it as 3n plus 5. Na? Okay. So we will be ignoring this 3. We will be dropping this constant value. We will be dropping this coefficient as well. We will be making it as n. We will call it as big O of n. Now, why big O of n? Why ignore this 3? If I take n value as 10,000, I know that in 10,000, if I calculate it, 3n would be 30,000 and that n value would be 5. So this 5 value we have. So 5 is having very less contribution in this 30,000. So we'll not be having this 5. We'll ignore it. But coming to 3, you see 10,000 or 30,000 are very big values. Okay. There is not much difference between them. So why should I drop this 3? That is our question. That is what we are trying to learn here. Now, as I said, we will be talking about how your algorithm grows. Now, see here how 2n or 3n or 4n will be. If I'm giving you n is equal to 10, you're going to take how many operations? You will be taking 20 operations, double operations. If I'm giving you n is equal to 20, you will be taking how many operations? 2n operations, 40. If I'm giving you n equal to 30, you will be taking how many operations? 60 operations. If I'm giving you n equal to 40, you will be taking how many operations? 80. Or if I plot a graph, this is how it will be. Now, how is it growing? It is growing linearly. How is it growing? It is also growing linearly. Okay. The rate of growth of your graph will be linear only. This is what we call as linear time complexity. Your graph shape will not change. Your graph shape will not change. It will stay linear only. Okay. So doesn't matter what coefficient you have, it will not affect it much. As I said, we will be always comparing different time complexities. We will not be going with n versus n. We will be talking about n versus n square also. We'll go through that. You will get a good idea about it. Ignore that. That graph is not designed yet. It's not completed. Now see here, as I said, for n value is increases, you will be able to get a good idea about it. Now see here, we'll be always talking about different graphs. Let's say you have an algorithm which gives you n complexity, and you have another algorithm which gives you n square complexity. Okay. You have n, you have log n. Okay. You have n square, you have n cube. So here we have a small error. Just a second. Here we have a small error. Sorry. This was completed just a few days back. Did not check it. So this is how we generally prefer the algorithms, whichever is having the lesson number. Okay. So n is better than n square. N is better than log n. Okay. N square is better than n cube. So that's how the general scenario goes, or you will understand it. See here. See this one. Let's come back to the same point here. Now 3n plus 5 we have. As I said, ignore the constant term. Why? Because its contribution for a very big n value. Let's say n value is 10,000. Okay. 5 is not contributing much in that 30,005. So you can ignore 5. So you can remove 5. Now we can also drop the coefficient. Why should I drop the coefficient? Because if you plot a graph, if you're talking about this algorithm with the other person, he will be asking, what is the rate of growth of your graph? You will be saying it is linear. Linear means if I increase my input value, the output number of operations will also increase linearly with it. For n, for 2n, for 3n, for 4n, for 5n, the graph is going to look the same. It is going to grow linearly only. Okay. So that's why you will just simply call it as linear. You will drop the coefficient. Okay. That's what we'll get as linear complexity or big O of n. Now, if I compare it, let's say you said, sir, I got one person's output as linear, the other person's output as quadratic. Quadratic in the sense n squared. Okay, this is where we can get n squared. Now we are still not done with it. We still have a lot of other equations. So see, then finally you can ask all your doubts. Let's say I have this value. How many lines, like how many operations will the first line will be? One operation taking input. Okay, one operation, sorry, displaying output, taking input, one operation. Now, how many operations will the first for loop will executed? The first for loop will be executed, as I said, 2n plus 2 you can write, or simply we will call it n plus 1. Sir, why did you drop that 2 and 2? Because coefficients, less dominant terms does not matter. So for simplicity, we just talk about it in this manner because ultimately I'll be removing all those less dominant terms. I'll be dropping all those coefficients. So even if I write it as 2n plus 2 or if I write it as n plus 1, it's the same only. Okay. I'm just writing it efficiently from here onwards. Let's assume the loop executes for n number of iterations or one more iteration for failing the condition. The inner loop will be executed how many times? The inner loop will be true for n number of times. It will be executing n plus 1 times again. Okay, so n into n plus 1 it is going to be. And what about the asterisk inside of it? Okay, so that print statement will be executed n into n number of times. This is nothing but printing a small square pattern. Okay, nested loop we will be writing. If I am giving you n is equal to 5, we will be getting a 5 by 5 square pattern. Okay, 5 by 5 asterisk we will be getting, stars we will be getting. So it will be executed how many times? N into n times the outer loop will be true, n times the inner loop will be true. So n into n times it will be executed. So if I'm giving you n equal to 5, you will be having 25 stars also. That's it. And what about the print statement after it? It will be executed some n times also. This is a simple square pattern that we are printing. Now, if you calculate the sum of all the operations that you are getting, okay, you see 1 plus 1 plus 2n plus so on, you are getting this equation here. Now, I need to talk to the other person about the time complexity of my code. I will not be including all these complex terminology in it. Okay. So how I can evaluate or how I can, okay, make this expression a little bit shorter. I'll be ignoring the less dominant terms in the sense if I take n value as 10,000 or so, imagine very big n value as 10,000 or so. So, or n value as 100 we will take. So 2 into 100 into 100, that is going to be 10,000. So 20,000 this is going to be plus 3 into 100. So 300 plus 3. You see in 20,303, 3 is a very small value, very less contribution. So ignore it. It's negligible. If I take n value as 10,000, it's going to be very big. As you have seen the percentage, this contribution is very less. And 300 also in 20,000, 300 will be very less. Or if you take n value as 10,000, in that very big value, 30,000 will be very less. So we can ignore this one as well. Now coming to 2n square, I told you to ignore the constant, sorry, ignore the coefficient, drop the coefficient. Why? Why? Because it doesn't matter. If I plot the given n value and if I plot the number of operations, this graph is what we call as rate of growth. Okay. Now, n square, if I'm giving you n value as 10, the number of operations it will take is 100. If I give you n value as 20, the number of operations that you will be taking is 400. If I give you n value as 30, the number of operations you will be taking is 900 or so. Let's plot a small graph here to give you that idea about it. I think I've erased it too much. Let's say we will start from 100 only. 100, 200, 300, 400, 500, 600, 700, 800 also. So if I'm giving you 10, so 10 into 10, it's going to take 100 operations. 20, 20 into 20, how many operations? 400 operations. 30, 30 into 30, how many operations? Okay, 900 operations. You see here, the graph will grow in a quadratic manner, in this curved manner. Okay, in this manner it will grow. Now let's talk about linear. If I'm giving you 10, it will take 10 operations. If I'm giving you 20, it will take you 20 operations. If I'm giving you 30, it will take you 30 operations. If I give you 40, 40 operations. You see, we are still not crossing it. Okay, see it? See, this is how the graph will be maximum. If I'm giving you 100, okay, it will take 100. But for this one, 100 into 100, it is going to take 10,000. You can see, imagine where that graph will grow. So this is big O of n. This is big O of n squared. So which one is better? Obviously, big O of n is better. Okay. So whenever I'm talking about time complexities, in order to ignore all this complex calculation, we simply talk about how the graph will grow. For the input n value, if my graph is growing linearly, it is better. If your graph is growing quadratically, okay, linear will be better than quadratic. This was is what we call quadratic. Okay, so this is how the graphs will be. Let me complete this session. Let's go through all of it. Then you will understand. So why do we ignore the less like constant terms? They have very less contribution in that very big value where n is tending towards infinity. 3 is a very small number. Ignore it. Less dominant terms also have very less contribution. Ignore them. Okay, coefficients, it doesn't matter. Okay, so the rate of growth of your graph, the shape of your graph will be the same. So coefficients also you can ignore. So the complexity is we go off n square or quadratic you can call. Or let's say if the complexity is linear, if I'm giving you n as 0, you will take 0 operations. N as 100, you will take 100 operations. N as 200, 200 operations. 300, 300 operations. 400, 400 operations. 500, 500 operations. With the given input value, if the number of operations that you are taking is also growing linearly, that is what we call linear time complexity, or that is what we call big O of n. Okay, linear time complexity. Now see the next one, the same graph for n square. If I'm giving you n value as 10, okay, it is taking 100 operations. If I'm giving you n value 15 to 25, n value 20, 400 operations it is. N value 25, n value 30, okay, 900 operations, 35, 40, 45, you see here, 50, it is taking 2500 operations or so. If I keep all these two graphs, if I plot all of these graphs, the constant time complexity, okay, logarithmic, let's ignore it a little bit. We'll talk about it in binary. You see, if I compare all these graphs and all that I'm getting, constant time complexity, okay, that linear time complexity, logarithmic, n square, n cube, n power 4, etc. If you write all of those graphs, this is how huge the difference is going to be. Okay, you see that is constant, which is not going to change depending upon the input. For any given input, it is going to perform the same number of operations. Now, coming to the next one, let's ignore logarithmic for now. Coming to, you see, big O of n, if I'm giving you 50, the maximum number of operations are being performed 50 only. Okay. Now, same thing, look the quadratic, how huge the difference will be in the graphs. Okay. If I'm giving you an equal to n squared time complexity, you see here for the same 50 you're taking 2500 operations, see how huge the gap is. So which complexity will be better generally? Big O of n is far better than big O of n squared. Okay. Big O of log n is better than big O of n. Big O of 1 is better than all of the above because it doesn't depend on the input value that you are giving. It will always take constant number of operations. So whenever we are talking about time complexity, we reduce that complex expression into one single term. We talk about how the input, like how the output number of operations grows with the given input value in simple terminology. And again, if you have listened to the lecture properly, whenever we talk about or compare n square versus n versus log n also, we will be ignoring the less dominant terms, etc. If I am getting one single code or two different codes which are having same n square complexity, I need to include that coefficient. I need to include that less dominant terms. I need to include that constant, like constant values. Okay, those all will come into picture. But whenever we are comparing algorithms, we talk about it in this simple terminology. Now, this is what we call big O complexity chart. Okay, green is for excellent, and that red is for horrible also. You can see here we have some mathematical functions for it. Okay, log n log n square. Okay, 2 power n, that is exponential time complexity, and n factorial we have. Okay, factorial time complexity. This is how everything is. So whenever you are coming up with the solution of anything, if you are getting constant time complexity, that's the best possible way of solving it. Okay, if you are getting it as log n also, that's another best way. We'll talk about binary search. If you are getting linear, that is also good. If you are getting it as n log n, that is also fine. If you are getting n squared, that's a bit bad, but that's fine. We cannot avoid it sometimes. But 2 power n or n factorial, these are the worst possible. You will generally not come across such type of complexities. Whenever you are getting a TLE, let's say you have written a code and the time complexity that you are getting is n squared. Okay, you're getting a time limit exceeded error in lead code, in hacker rank, in geeks for geeks, all these platforms and all. You need to try and reduce that n square complexity into n log n or big O of n or log n or O of n. Okay, means for the input, the number of operations that you're going to do will be less. Means the time taken for to complete those operations will be also less. So that's what we have. Okay, so there is one more thing where we will be needing this. Whenever you study any algorithm, they'll be talking about best time, average time, worst time, okay, or what is the time complexity of it. Why? Because whenever you go through a question, okay, they will be mentioning in the constraints about the size of the input, means how much input you can expect. For example, okay, let me show you. This is how it will be. In the constraints, they will mention that the given n value can be from 1 to 10 to the power of 5. Means you must write an algorithm which can handle up to 1 lakh operations also. 10 to the power of 5, I think, yes, 1 lakh operations also. Now, if the input n value increases, let's say you are taking n value as 10 to the power of 18 or 10 to the power of 20. Okay, if I'm taking a very big value, then the number of operations that you are taking should be very less, because for n tending towards infinity, you need to select an algorithm which is giving you better time complexity. Let's see what I mean by that. Okay, you see our machine can perform 10 to the power of 8 operations per second. So whenever you're getting a time limit error for any complexity that you have written, you need to try and reduce that. Let's say for n square, you're getting a time complexity, try and reduce that to n log n, or try and reduce that into big O of n, or try and reduce that into constant, okay, or log n, whatever it can be. Or whenever you come across algorithms, okay, they will be mentioning time limit, they will be mentioning that worst case complexity there, or let me show you a small graph related to it. Let's say if the input n value is 10 to the power of 18 or so, okay, which complexity you will be using? You need to go with log n or big O of 1. Okay, you need to perform the solution very quickly. The number of operations should be very less. So we'll be going with binary search, or we'll not be using any loop. We will be directly calculating it through the formula also. Okay, imagine we need to calculate sum of n natural numbers. There are two ways of generating it. Either I can use a formula, or either I have to generate all numbers from 1 to n. I need to calculate sum of all those numbers from 1 to n. Okay, and then I need to display it. Done. These two are correct solutions. But for 10 to the power of 18 value, okay, if I generate 10 to the power of 18 values, it is going to take a lot of time. Okay. So if I'm getting a time limit exceeded error, that solution is correct, but it is taking more time. There is a very efficient way of writing it. We will be going back to direct formula. We'll be trying to reduce the time complexity. That's what I'm trying to convey here. If they are giving you 10 to the power of 8 operations also, like if the n value is mentioned in that manner in the constraint, you can happily use linear search. That's what you need to look for in one single iteration. You need to, in one single traversal, you need to try and complete the equation. Okay. If they're giving you 10 power 6, n log n is fine. If they're giving you 10 power 4 operations, means very less number, like the n value is very less, 10 power 4 means you can use a nested loop. Okay. Nested loop, these things are all bubble selection, insertion sort. You can use these type of things. If they're giving you 200 values, you can go up to n square log n. Okay. If they're giving you 400 values, you can go with n cube, n power 4 exponential, even factorial time complexity is also possible. We'll be talking about them in recursion and all. Okay, so don't worry. For now, the total conclusion of all these things is whenever you come across any question, whatever solution that you write, count the number of operations, try to simplify that expression, try to come up with the most dominant term you have. Ignore coefficients, okay, drop all coefficients, ignore less dominant terms, okay, drop those constants, etc. and all. If you are getting a time limit exceeded for it, then if you are getting time limit exceeded for n cube, try to reduce that to n square. If you are getting time limit exceeded for n square, try to reduce that into n log n or n or log n. You need to go with a better time complexity. And one more point, whenever in the input constraints they are mentioning any n value, if they are telling you that I'll be giving you 10 to the power of 18 values, which is very huge by the way, you need to try and use a direct loop for it, sorry, direct formula for it, no loops, or you can either go with binary search, that is also very efficient, log n it will be. If they are giving you 10 to the power of 8 values, try to use linear search. Only one loop, one iteration, one traversal, you should get the answer. If they are giving you 15 values, input only up to 15 values, you can also have a loop inside a loop inside a loop inside a loop inside a loop. Okay? Or you can have factorial time complexity. 15 factorial is not a small value, it's going to be a very big one. Okay? So you can also use factorial time complexity for it. That's what I'm trying to talk here. Okay? So depending upon constraints, you will be selecting an algorithm. Or for a given answer, if you are getting TLE, you need to try and go with a better complexity one. This is how you will be evaluating it. Don't worry, we will be solving some questions. You will understand how to evaluate time and space complexity properly. Now let's take some quick examples on these constant time, logarithmic time, linear time, quasi-linear time, okay, exponential time, factorial time. And we also have other time complexities. We have n cube, n power 4, n power 5, n power 6, whatever mathematical function that you can think of. You see, I have just given n log n. We have n square log n cube log n. Okay, and this log is also base. You can have base 3, base 4. So that's how things will be. You just need to calculate for a given n value. If it is taking constant number of operations, constant time. If it is taking, okay, quadratic number, like square number of operations, that is quadratic, square. If it is taking same number of operations, that is linear. It's always about the rate of growth of that graph. Now let's see what is constant time complexity. Let's take a small example. Okay, see here, if the number of operations does not depend on the input that you are taking, okay, does not depend on the input size, that is what we call as the constant. Let's say we have biggest of two numbers checking also. How many operations will it take? Only two operations. One operation it will be checking it. One operation it will give us true or false. That's it. It doesn't depend on the input size. It doesn't matter what values of A and B you enter. You will always get how many operations? You will always get two operations only. That's it. Okay. That's an example for constant time. Okay. Big O of one, the complexity will be. Now let's take one more example. Where can we get logarithmic? You see, for binary search, we'll be talking about binary search. Don't worry, in arrays we'll be having it. Now, in binary search, in every iteration, we are going to reduce the number of iterations by half, the number of elements by half. Okay, the elements that we want to search for will be reduced by half. I hope you are a little bit familiar with binary search. If not, don't worry, we'll talk about it. For now, let's say we have an array of 10,000 elements or so, sorted values, all of them are. Okay. So in these 10,000 elements, in the first iteration, I'll be removing half of it. Okay. 10,000 will become 5,000. 5,000 will become 2,500. Again, half, 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 half or so. Okay. So every time we are eliminating half of the values. Now, how many iterations did I do in order to reduce or in order to make it one? That is logarithmic. That is log of base 2. You will be taking a maximum of, I think, for 10,000, it will be somewhere around 13, 14 operations. That's how it will be. Okay, maximum of. We'll talk about logarithm, don't worry. But every time if you are reducing the input, like the number of operations that you need to do by half, that's what we call logarithmic. Okay, so you will be able to reach it in 14 steps or so. That's log of base 2 of 10,000. That is 13.28 or approximately 14. You can say that's it. 13 to 14 steps it will take. We'll talk about it very clearly. Binary search. We have a separate section for it in our arrays, so do not worry about it. That's it. Done. So what is the time complexity? What's an example for logarithmic time complexity? Binary. Now let's talk about linear. Linear is pretty simple. You see, let's say I have an array of n elements. If I'm performing traversal, I need to go through all of them. I need to perform n number of operations. So if you have 10 elements, I need to perform 10 operations. If I have 100 elements, I need to perform 100 operations. Or let's say I have to generate n number of values. The loop will run for n times. So that is nothing but linear time complexity it is. That is linear time complexity it is. Now what about quasi-linear? Means, let's say for every time you're performing okay, binary search, or for every time you're performing or you're dividing the number of elements by half, okay, in another array, or in merge sort, in quick sort, etc. and all, okay, you'll be dividing them log n times, so you'll be having n log n in that. Okay, I know merge sort, quick sort, some of them worst case will be n square, but that's fine. We'll have the discussion later on. Now coming to quadratic time, whenever you're trying to display any pattern, okay, let's say matrix, you have an n by n matrix, you are trying to access all the elements. N by n means if I am giving you n value as 5, in order to generate a n by n pattern, or let's say you have a matrix of 5 by 5 size, so you have 25 elements in it, or you have 25 stars that will be displayed. You see this one, asterisk we are printing, we have a square pattern. I need to print asterisk how many times? If I'm giving n value as 5, asterisk will be displayed 25 times. If I'm giving n value as 10, asterisk will be displayed 100 times. If I'm giving you n, it will be displayed n square number of times. Okay. So if you have a loop inside a loop, I hope you remember, we have calculated all of it. We have removed all the, okay, complex terms. You can write it as 1, n plus 1, n, again 1, n plus 1, n. This will generally run for 2n plus 2 times. But this is inside another loop. So this will make it run for n times. So this is going to run for how many times? 2n plus 2 into n. And outer loop will run for 2n plus 2. So 2n plus 2 plus 2 into n square plus 2 into n. So you see, we have a very big equation. 2n square plus 4n plus 2 we have, as I said, ignore the constants, ignore the less dominant terms, drop the coefficient. So what is the complexity of it? N square. Now, again, you might be having some more doubts in it. This will take you some time to sink in all the details. Okay. When I am talking about this algorithm with the other person, let's say the algorithm complexity I got, grading I got is n square. The grade he got is n. So which one is better? Which one is better? Always big O of n is better. Okay. When I am talking about, let's say the other person is also getting n squared, then I'll be comparing what was your constant, what was the contribution of your less dominant terms, how many operations is it taking. But mostly, whenever we compare algorithms, we go with, okay, two different algorithms. We'll compare n square versus n or n square versus n cube. This is how we generally go about with it. Okay. So coming to quadratic time complexity, an example, that's matrix you can take, or this one we have. Just a second. Just a second. I need to adjust my laptop a little bit. Oh, okay. Done. Now, okay. So it is going to be executing n number of rows and n number of columns every time. So this is n square complexity we have. Okay, that's it. Quadratic time complexity. Now exponential time complexity. We have very good example for this. Fibonacci series we have. Okay, that's one good example. We'll talk about it. Let's say for n is equal to 1, you'll be having only one call. For n is equal to 2, you'll be having two calls. For n equal to 3, four calls. N equal to 4, eight calls. N equal to 5, 16 calls. If you slowly increase the number, that is going to be a power of that 2. It grows exponentially. That is 2 power n it is going to be. Okay, we'll talk about it in recursion. Don't worry, I'll show you a very, very good visual representation of recursion that you might have never seen. But now exponential, this is very rare and this is going to take a lot of time as well. You'll understand that in recursion. Okay. Now let's take about factorial time complexity, calculating permutations, etc. and all factorial time complexity. Okay. Very rare actually. And let's see if I'm giving you one value, how many different ways of arranging it? There is only one way. Okay. If I'm giving you two values, A and B, how many different ways of arranging it? A, B, and BA. So two values. So that is 2 factorial. Okay. If I'm giving you three values, how many different ways of arranging it? That is six different ways. So nothing but 3 factorial. If I'm increasing one more number, if I'm giving you n equal to 4, how many different ways of arranging it? There are 24 ways of arranging it. That is 4 factorial. If I'm increasing one value, the number of operations will be increased by factorial ways. This is what we call n factorial. And this is going to be a nightmare if we cross 15 or 20. It is going to be a very huge number. These are generally rare. These you will never be coming across. Just to show you a small example that you can have any type of complexity, it's all mathematics. Okay, n square, n cube, n power 4, n power 5, 2n square, 3n square. You can ignore all the constants. So n square log n cube log n. So it can be anything. Okay, so it's always about comparing them. We need to go with the lesser value in the sense, lesser value in the sense. You see, okay. If you are having n factorial, n square is better than that. If you are having n square, n log n is better than that. If you are having n log n, big O of n is better than that. If you are having big O of n, log n is better than that. If you are having log n, constant is better than that. So whenever you are coming up with a question, or you are coming up with a solution, you will be calculating the time complexity. You will be simplifying the equation to the most dominant term. Okay. If the value that you got, the complexity that you got is n log n, and the other person got big O of n, which one is better? Big O of n is better. Let's say you have two or three different ways of solving it. You will be calculating the number of operations. You will be getting that equation. You will be reducing that equation by ignoring less dominant, removing coefficient. Okay. So all in all, then you will be grading it. Just like we have O grade, A grade, B grade, C grade, D grade. Doesn't matter if you are getting 92, 93, 94, 99, etc. You will be into O grade only. That's what we are doing. We are making it simple. We are talking about whenever we are comparing algorithms. Okay. We will talk about the rate of growth, how the algorithm will grow with the input n value. Okay. We'll not be talking about all the other complex equations. If I'm comparing two algorithms of the same time complexity, then I'll be including those less dominant terms, those constant values, which is pretty rare and which we don't generally do. Okay, we compare different growth rates. As you have seen that growth rate of n versus n square versus okay log n. That's how huge the difference is going to be. So we don't even have to compare the same time complexities ones. We are only interested in the different ones. That's it. That's about time complexities. As I said, you will be having any mathematical imaginable values that you can get. Okay, n powers of anything. That's it. That's a little bit about time complexity. That's a little bit about how to calculate time and space complexity. Done. Any doubt? Any doubt in this? Any doubt in any calculation? Any doubt in anything? Understood about how to come up with the number of operations of any given algorithm or question, how to reduce it, or what we are looking for in time complexity, what we are looking for in time complexity. So generally, you see, when we are having two big O of one algorithms, we don't compare. Big O of one is very efficient, and your system performs 10 to the power of 8 operations per second. And if you talk about it in that way, you see here, actually things work a lot differently. Okay, if I'm writing A equal to 1, it's not one single operation. I need to go inside my system machine. I need to search for that value. Or if I'm writing a equal to a plus 1, I need to fetch that a value. I need to add 1 to it. I need to again store this a value inside that memory location. So it's not actually a constant time. Okay. It's not actually one operation. It's going to take more than that. So you don't have to go that deep until and unless you're doing some research or some advanced certification in it. It's not required. Okay. So for now, keep it very simple. Whenever you're having any algorithm, calculate the number of operations you are getting, simplify that expression. If your expression is n square and the other algorithm that you have is n, which is better? N will be taking less number of operations. It will take less number of time to execute. Okay. Any doubt? Any doubt till this point? I think the meeting, yeah, it is set to host and co-host. So I'll set it back to meeting group chat. So any doubt till this point? Anything that you want me to explain away? I hope you understood about how to calculate time, how to calculate space a little bit. In time complexity, we'll not be talking about the actual time. We'll be calculating the number of operations we are getting. Okay. Any doubt? Any doubt till this point? Can we continue? Any doubt about the constraints? Yes, let's go back to it again. You see, coming to the constraints part, don't worry, we will again open lead code, we will solve some of the questions there. In the constraints, if they told you that the n value I'll be giving will be up to 10 power 8, you need to try and use only binary search. You need to try and use only direct formula. Okay. You should not be going with a nested loop or even a loop as well, because it is going to take lot of operations. You will get time limit exceeded error. Okay, if you are someone who is new to lead code or competitive coding platforms, we are going through all of it, so don't worry. Okay, so if they are mentioning you, I'm going to give my input n in this range. This is what suitable algorithm that you can come up with. This will not be giving you any time limit exceeded error. Done? Clear? Any doubt? Anything else that you want to talk about? So talking about optimization, you see, coding is all about recognizing patterns. Okay. So that's where people generally practice and lead code, etc. and all. Take any pattern or take an array, for example. Okay. When we take any algorithm, two pointer, prefix sum, sliding window, etc. and all, if you solve a set of questions, 10, 20 questions per algorithm, You will be able to learn everything related to the algorithm, when you can apply that, what that algorithm generally does. So when you practice frequently, when you are in that zone, whenever a question is given to you, you will be able to solve it in multiple ways. Multiple ways in the sense, see, I have given you for this simple question, I wanted you to calculate sum of n natural numbers. There are two ways of solving. Okay. And into n plus 1 by 2 formula is there. We can generate n values. We can calculate the sum of it by using a loop. Two ways are there. Now we have two different ways. How these two different ways came into your mind? Okay, because we have been practicing them. We are at that starting level or medium level. We pretty well know about all the different ways of solving these basic loop questions also. Same thing happens as well with arrays, strings, etc. The more time you spend with coding, the more questions you solve it, the better you will get at that recognizing the algorithm, recognizing the optimized output and all. You just need to practice a little bit more. Okay, slowly it will come. You don't have to think about it that much. It will come to you naturally only. Okay, that's it. Will we be talking about those patterns? Yes, we talk about two pointer a little bit in linkerless. You have a good syllabus, so we will be going through some of those questions. Okay, not much because 30 hours, 2 hours per session, we still have 26 hours or so pending. Okay, we need to cover a lot. Not much, but you will be having a bit and piece of it everywhere. We'll be talking about different other questions as well in every data structure. We'll be having a piece of everything. Okay, that's it. We'll go through some of them. Done? Done? Yes, I'll do that at the end of this 30 hours training. So I'll give you a detailed roadmap of what algorithms you can learn. Okay, how much time will it take? You can get all those details. I'll give you at the end of the 30 hours. Last day, we'll talk about all these things. For now, we'll not have any of that. Okay. For beginner, you can start with either Hacker Rank. For beginner, you can go ahead with Code Chef if you guys can pay 5,000 or so. I think Code Chef membership is for 5,000. So you can use Code Chef. You will be able to get that certificate as well. Okay. Or Hacker Rank will be fine. You will be having simple questions. You will be getting badges. Okay. Depending on the number of stars you get, that will motivate you a little bit. Lead code is a bit advanced only, but as I have shown you, I have saw a lot of questions in it. I have collected all the basic questions in lead code. You can also go through lead code as well. Okay, you just need to look for the right number of questions. Okay, in the next session, I'll be giving you some basic lead code questions as well. You can also go through it. Any platform, it's the same. If I have to give you a suggestion, CodeChef. Okay, free platform, like free questions are also there. Basic if else, basic operators questions are there. If you wanna explore a little bit without paying money, Hacker Rank you can get started. But ultimately, everyone has to come to Lead Code only. Lead Code is very good. Okay, Geeks for Geeks is also a very good platform, but I prefer Lead Code a little bit. Okay, so if I have to rank based on how good the platforms are, Lead Code will be always ranking one. And on the second place, maybe I'll be having CodeChef. Okay. And third place, I'll be having Geeks for Geeks. Last, I'll be having Hacker Rank. Hacker Rank is for pure beginners. Okay. You can get started with it. And not much into, like, you will be able to explore the world of data structures and algorithms, but not up to competitive coding. Done. Prime factorial, no, not here. We will not be able to talk about it in this session, maybe some other time, or you can try and connect me in LinkedIn. I'll give you a solution there. Yes, we'll be going through Java only. I got that, but my presentations are generally in Java. You will have that in Python, so don't worry. In anyway, we are not talking about any code. We are only talking about how many operations it will take. Okay. For second year student, which DSA topics? Okay, not DSA. You can go with DS. Means you have to know up to graphs. You now have to know up to trees. The basic implementation of how depth first search, how breadth first search executed, tree traversals. What is a binary search tree? If I have to talk about algorithms, linear search, binary search. Okay, all five, six sorting algorithms: quick sort, bubble sort, merge sort, okay, selection sort, insertion sort, count sort, bucket sort, radix sort, you can go. So all good sorting algorithms you have to complete. That will be enough if you are in 2-1, 2-2. But before you get started with third year, you need to again start a little bit of more focus on recursion, backtracking, dynamic programming, greedy algorithms. Okay, that's what you can do for. No, presentation will not be shared. My presentations are of high value, so no, it will not be shared. You can take a good note of it. Uh, that's what. Yes, this class is recorded. Na? You are getting the YouTube link, YouTube channel, XLR YouTube channel. You can go ahead and watch the class again. No, last day I'll be sharing the roadmap, not today. Okay. Presentation will not be shared. Class is recorded. It's already on YouTube. You can check it out as well. Coding contest, you need to know all coding concepts first. Otherwise, you will be able to solve half of the questions only. If they are giving you four, you will be able to solve two. If they are giving you six, you will be able to solve three. Until and unless you know up to dynamic programming, do not enter any coding contest. As a beginner, if you want to give it a try, you can, but you will be only solving half of the questions. If you know dynamic programming, greedy algorithms, backtracking, all these sliding window technique a little bit, you can happily get into them. But otherwise, no. Constraints will be always specified. Okay, in a question, constraints will be definitely given. If not, it's a basic question only. If not, it's a basic question only. Okay, constraints will be always given in any question. A runtime error means, you see, compile time means when you are writing the code, if you are coming up with any syntax related issues and all, then it will not be able to convert that into zeros and ones, machine understandable code. That's what a compile time error. Runtime means syntactically everything is correct. Because of the input that you are giving, it is going to get an error. For example, I have division of two numbers, a divided by b. If b value is 0, during runtime I'm entering b is equal to 0. So because of that, any number divided by 0 is 0 division error. That's a runtime error. Okay, you can simply Google this stuff. Everything is at your fingertips. You will be able to get a good example. You will be able to know more examples. Okay, compile means, simply speaking, in a one single line, whatever code that you are writing, if it has some syntax related issues and all, okay, rules of the programming language, then it's unable to convert that into zeros and ones. That's what we call compile time. Runtime, because of the input that you are entering, if you will be ending up with some sort of error, maybe the database connection is not successful, if I have to talk about it at high level, or at low level, zero division error, dividing a number with zero. Okay, that's one thing. Syntactically, everything will be right, but while running it, because of the input, you will be ending up with a error. I'm left over 3 months of my campus. It's never late to start. You can, it depends on the packages that you are eyeing for. If you are only looking for 3, 4, or 5 packages, 5 LPA, basic of any programming language, a little bit of DSA will be fine. If you want to get high packages, you need to know each and everything. So depends on which packages you are looking for. If you are looking for 3.5, 4 LPA, 4.5, one programming language, a bit of basics of DSA will be fine. How much hours? As many as you can. Okay, it's easy. It will be fun. So as many as you can. As many as you can comfortably. Okay. And it's not like this many hours you have to sit. It's about if you can spend 1 hour, if you can highly concentrate, understand, process things, 1 hour. 2 hours, if you can sit and code for 2 hours with high concentration, 2 hours. Otherwise, it's good for you to go and watch a music, watch something on the TV or listen to music. Okay, it's about that interest. It's about how good you are. You should be in a good space. Have some coffee or chat with your friends or play something and come back. So it's not like how many hours. It's about how well you can concentrate. Or if I have to give you a number, basically, I would say 1.5 hour to 3 hours will be a very good time. Every day you can spend on it. You can solve one or two questions. You will be able to get a nice idea of the concepts. Just a second, my battery is running low. this is gonna die. Sorry, maybe the battery will die. Which language is more important to learn? It's Java. Java is more important to learn. Okay. Java, you will be getting good programming concepts. Python is easy to learn. Python has its own applications in AI, ML, etc. You need to start learning Python. Java is superior. If you ask my opinion, Java is superior. Okay. So I would prefer Java everywhere. That's why you can see Java code in my presentations. How much math? You need to know seventh grade mathematics. That's it. In order to learn coding and DSA, you need to know seventh grade mathematics. Nothing more than that. Okay. Seventh grade maths will be fine. Last day, I will give you all the important algorithms that you need to learn. Okay. Not today. Yes, graph is a very non-linear topics are very important. Non-linear data structures are very important. You need to know non-linear. That's where we will be having all complex implementations. If you are a beginner, if you don't know much know about programming, start with Python. If you are comfortable, if you know a little bit about programming, you can go ahead with Java. Okay. DSA with Java is always better. So that's what I would prefer. As I said, Java is superior to me in my perspective. Yes, any idea about? Yes, we have, but C programming, I would not generally prefer it. C++ is fine, but C programming does not have object-oriented programming concepts. So go with C++ if you want. Ultimately, Java is what I prefer for DSA. If you are a beginner, go with Python. If you are someone who is into C++ competitive coding, you can use C++. C++ is generally fast in execution. That's what we see in time and space complexity. So fine. Java would be better for your projects, for your career. Okay. So Java would give you all programming concepts. Java, you can do good development. You can get into full stack Java. Okay. You can learn all good like multi-threading, object oriented at a good level. Okay. Exception handling, all these things in Java better. And in any company that you work for, you might need to work in Java. So Java, that's it. Which languages? You see, every language has demand. It's about how knowledge you have. So if I talk about normal programming language, it's gonna be Java first. If you are getting into machine learning, AI, etc., and all, you need to know Python. If you are getting into full stack web development, it's going to be JavaScript. JavaScript has the libraries React, Node.js, and all. So that question is generally not answerable. Okay, we cannot answer it. It's about the programming concepts. If you know all the good programming concepts, you can happily get any job. For high paying jobs, you have to be good in one programming language, preferably Java. DSA, you have to be good at, and development. That can be full stack development. Your GitHub should be full. You can get into a little bit of machine learning. Okay, build some projects. That's what they will be looking for. But one programming language and DSA, preferably Java it is. That's what I prefer. You can start with Python. There is nothing wrong with Python, but it's my personal opinion. I'll always go with Java. Companies in written exams, they will be going with dynamic programming greedy because they will be there are dynamic is the most efficient one. Okay. So and they are a bit harder to get a hang of or recognize. So companies they can mostly ask you DP, greedy, these type of questions. Okay. Depending on the package, it will be, but high packages, if harder questions, DP and greedy. That's what they can ask. Done. Core Java or advanced Java. It's core Java is nothing but a small first piece of it. Part one, part two, you can say that's entire Java. Core plus advanced is entire Java. Okay. IT market defines what subjects in the sense? No, I did not understand that question. Combination of a subject. No, you got me lot of queries. Hey, I have started the queries only for 3 4 minutes, man. You have been asking it for last 20 minutes. Why not C++ over Java? Because as I said, Java you can do good development. Full stack Java you can get into. Okay, so You need to look for one language where you will be able to do DSA, where you will be able to cover your interviews, where you will be able to build projects. So preferably Java. Okay. C++, generally, if you are into game development, etc., and all, you will be using C++. If you are someone who belongs to ECE, Triple E, you will be needing C++ a lot because all the operating systems, okay, device drivers, these things will be written in C++, right? So you can get into it. It depends on which field that you are looking for. You see, C is designed for a specific purpose. C++ is designed for a specific purpose. Java, Python, they all have their own use cases. They all can do all the tasks, but some of the applications can be built by majority by those languages code only. It's about which language, like if you are gonna be a machine learning engineer, you will be starting with Python. You will not start with Java. No? That's the difference that I'm talking about. Okay, it's about you. Asymptotic notations means the graph mathematical notations that we use, the graphs that we are talking about. Big O is a part of that asymptotic. Asymptotic means approaching a curve. Okay. So Big O talks about worst case scenario. Big O is the one that we need. We need to always give the user the worst time complexity because it will not be exceeding that worst case. Imagine, remember that box? Let's say I built a software where the user will guess a number. The what you say that for the client I'm telling like I have n number of balls here. Well, like can I say that if you guess a number you will get it in two iterations, five iterations, 10 iterations maximum, it will take you n number of operations. We need to always talk about worst case scenario. DSA with C, no, because C has no oops concept. Okay, so go with data structures and algorithms with something that you can build applications with, something which covers all your interview related questions, with something that is having object oriented programming. That's what I'm talking about. So all this is fine. I think I have taken enough questions for today. I see I cannot answer 500 people's questions in one single thing. So how much of DSA means, I think no amount of DSA. That's not required for you if you are getting into data analytics also, my opinion. You need to be good at projects. You need to be good at mathematics. Okay. So a bit of everything will be fine. C is never dead. You will always have C. So don't worry. So I think that will be enough. That is fine for today. Questions that I'm taking. So tomorrow we will be going through some simple logics. We will be talking about functions. We will be talking about recursion. Okay. There you will be understanding a bit more about time and time complexity and all, which is better code and all. You will understand it there. So don't worry. Think I'll yeah have a small charging issue. Sorry for that. I need to adjust it a little bit. Yeah, done. That's it. So you cannot compare these languages. Okay. So don't even go ahead and comparing them. Java, data analytics, data science, etc. and all. No. Like you guys are at home only, right? You have all the break. You can just listen to the class, do whatever you want. So I'm the one who is speaking. So generally, no break, but maybe from next session onwards, since we are getting into coding, you will be getting a little bit of break there. I'll be giving you some time to think about the algorithm. So that's it. Thinking of these questions, we will continue tomorrow. I know algorithms like time complexity, space complexity, the asymptotic notations, these are all very big names for you, but it will become a bit easier. Okay, ultimately, at the end of the day, we will take it very easy. This is not even such a big topic. This is all about the theory that we have in it. We'll simply have a piece of code, we'll simply evaluate it in a matter of seconds. So don't even bother. Okay, it's very easy. And once we solve a set of questions, you will understand it. We will, for every question that we are doing, we'll calculate the time, space. We will compare which one is better. You will automatically get a hang of it. So don't worry. Okay. You have this lecture on YouTube. You can again go through that. I have a small disturbance here. Just a second. Yeah, that's it. I hope I've addressed all your queries. That's it. That's it for today. I don't have any charge on my laptop, so I'll be ending it now itself. That's it. That's it for today. We'll continue tomorrow. We'll go through some basic logics that we see and functions and recursion. Then, bye bye. Stopping it. Is there anyone else we have? I can only leave the meeting. Huh? Am I the co-host? Yes, it's me. Maybe she's the co-host. Host. Done then. I'll be closing this session now. Bye bye.